All right, so on page 67, we're going to talk about infinite limits and limits at infinity. We've seen kind of so far this year how the infinity symbol can kind of show up in different spots. For instance, we could have a limit approaching infinity. We've seen that before if we're traveling to the right or to the left. But we've also come across some things where a limit equals infinity, meaning going up, or negative infinity going down. So what we're going to take a specific look at in this section is if a limit is approaching infinity, what does that signify? And if a limit is or equals infinity, what does that signify graphically? So we're specifically looking at this infinity idea in this section. So we know we've dealt with rational functions before, asymptotes, wholes, all those good things. What we're going to do, let's see here. In terms of the phrase infinite limits, that's when your function equals infinity. So we're going to just do a little quick definition down here. An infinite limit is a limit that equals either a positive or a negative infinity as your x value is approaching some number. So graphically speaking, if we are referring to an infinite limit, okay, a limit equals positive or negative infinity, what is going on graphically? If you were to approach a number from the left and the right, and your graph either goes up or down, what's happening graphically? Yeah. There's an asymptote, okay? So this is signifying some type of vertical asymptote. So let's take a look at these limit examples at the bottom. If you were to approach 2 from the left, notice how we are approaching a number. What would the limit value be? 2 from the left? Negative infinity, okay? That is an infinite limit. Since your limit equals an infinity value, there must be an asymptote, a vertical asymptote at 2. Since you got infinity as an answer for your limit, there is a vertical asymptote at 2. What if we were to check out 2 from the right-hand side? The limit would be positive infinity because we go up. Again, since our limit value is infinity, we have a vertical asymptote at that x value we are approaching. What if we were to approach negative 1 from the left on the G graph? So this is the other one. If we were to approach negative 1 from the left, notice how we would go down. So there must be a vertical asymptote at negative 1. Even without checking the right-hand side, we already know there's a vertical asymptote there. That's the only thing that causes a graph to go down as you approach a number. Okay, so there must be one there. Even if we did check the right-hand side, though. Right-hand side of negative 1, we go up. So there must be a vertical asymptote at negative 1. So in terms of infinite limits, if your limit value is infinity in some capacity, either positive or negative, the x value is a vertical asymptote spot. We're eventually going to get away from looking at graphs, because notice how if we just had these limit values, we could determine that there was a vertical asymptote. Okay? Limits at infinity are kind of switched. So in this case, a limit at infinity is a limit in which the x approaches either positive or negative infinity. So instead of equaling positive or negative infinity, now you are approaching it in terms of how you trace your graph. So graphically speaking, if your x values were to go towards positive infinity or negative infinity, what might be happening on your graph? If we were to approach positive infinity or negative infinity, what are we approaching on this graph? Yeah.
2.
You're approaching 2, which happens to be the horizontal asymptote. Notice how infinite limits were vertical asymptotes, so the limits at infinity are the horizontal asymptotes. All right, so let's take a look at some of these. On the F graph, which is our first one, if we were to approach positive infinity, looks like Joseph said we would level off at 2. So what this limit is telling us is we have a horizontal asymptote at the y value of 2 specifically to the right. Because notice how we were only checking the right-hand side. We were only traveling towards positive infinity. So we have to state to the right. We're going to see some instances of graphs where we have 2 different horizontal asymptotes. Maybe we approach 2 on the right-hand side, but we approach something different on the left. Okay, so we have to specify which direction we were actually traveling. If we travel towards negative infinity on the F graph, we're also going to approach 2. So we have a horizontal asymptote at the y value of 2 to the left. So in this case, the horizontal asymptote is the same on both sides. That might not always be the case. All right, let's check out the G graph. If you were to approach positive infinity, trace your graph to the right. Can you describe the height of the graph? Yeah? It's actually going towards infinity. Notice how you're not leveling off at a value like we did before. You're traveling up forever. So what's that telling you about a horizontal asymptote? Do we have one? Are we leveling off? No. So there's no, we'll say no HA. There is technically an asymptote though if we look at the graph, right? Do we remember what that kind of asymptote is called? Yeah? A slant asymptote. Good. Okay. So just because it's going up forever, it might not always be a slant asymptote, but in this case, graphically, we can see that. Okay. But what this is telling us is that there's specifically no horizontal one. Okay. It might be slanted. It might not be anything, but there's no horizontal. Very similarly, if we check negative infinity, if we trace the graph to the left, we're not leveling off anywhere at an asymptote, so this would be negative infinity. All right, so moral of the story, infinite limits tell us locations of vertical asymptotes, whereas limits at infinity tell us something about horizontal asymptotes. Now, just for kind of vocabulary purposes, horizontal asymptotes sometimes can be referred to as end behavior. For instance, if you travel to the right end of your graph, what does it do? If you travel to the left end of your graph, what does it do? So if you come across that phrase end behavior, it's basically asking you, are there any horizontal asymptotes? Okay, it's just a synonym. Okay, something that means horizontal asymptotes. Are we doing okay? Hopefully nothing new. Okay, we're focusing on this idea of infinity in terms of our limits. Okay, so let's go ahead and try to move away from graphs. Let's try to analyze some infinity limits, either approaching infinity or equaling infinity, just looking at the functions. So what's our first step in a limit? Substitution. Okay, let's go ahead and try it. If you were to plug in 2 for all those x's, You get 0 over 0? Or something different? Yeah? 28 over 0? Okay. So what should be happening graphically at that x value of 2? There's a vertical asymptote. Okay. So we know that since there's a vertical asymptote there, the answer to this limit should either be positive infinity or negative infinity, because we're either going up or down. Now, we got to pay close attention to the notation as well. If that little minus sign wasn't there, your answer would be does not exist. Because as you approach a vertical asymptote from both sides, they're never really going to meet up, right? But since that negative is there, we have to check just the left-hand side. So our answer should be either a positive infinity or negative infinity. How do you want to try to figure out which one it is? We've done a few of these before, but now we're actually diving a little bit more into them. How can we check the side of an asymptote? Yeah. We're going to put in something to the left of 2. Yep. Pick something to the left of 2. Like 1 or 1.5, something like that. Okay. If you were to plug in 1 or 1.5, would the top be positive or negative? Positive. If you were to plug in 1 or 1.5 down below, positive or negative? Negative. So which direction is the asymptote going on the left-hand side of 2? Positive divided by negative? We got negative, so we're going down. This is an infinite limit. As you approach a number, you are equaling some type of infinity, in this case negative. Okay. Let's go ahead and check out the right-hand side. We still have the same equation, which means we're going to get out 28 over 0, signifying an asymptote. If we only are concerned with the right-hand side, we know we should be getting an infinity value. So let's pick something to the right of 2, like 2.5 or 3. If you plug that in up top, you'll get something positive. Plug in that number down below. You get something positive as well. So it looks like on the right-hand side of 2, the graph goes upwards. You remember doing those? Okay, they're coming back. Can you guys try the bottom 2? Go ahead and plug in -1, see what you get. Can we get positive infinity on the right and negative infinity on the left? Check it out. Okay, so we must have a vertical asymptote, not because of that number over 0 like we've discussed, but now we are actually calculus-wise showing it, okay, using the limit. The fact that we approach a number and we get either positive or negative infinity is signifying that location of a vertical asymptote. So we got to be careful, especially when it comes time for justifications or explaining certain things. You can't say anymore because we got a number over 0. Okay, you have to use this analysis, okay, the calculus notation or meaning. So as you approach a number, if you get infinity in some way, you have a vertical asymptote. Okay, so graphically, an infinite limit always yields a vertical asymptote. In pre-calculus, okay, last year, you guys observed that when you would factor the top and the bottom, and you were left with a vertical asymptote, that factor would not cancel out of the denominator. We remember that other way of finding a vertical asymptote? Okay? So from this point on, you can't say there's a vertical asymptote because you get a number over 0, but you cannot also say it's because you factor to cancel out or factor out. You have to show that it equals infinity in some capacity, okay, for the existence of a vertical asymptote. So as our formal definition of a vertical asymptote, we're going to say x equals a is a vertical asymptote only if, okay, this is what you have to show. The limit as you were to approach a from the left is either positive or negative infinity. That would suffice. Okay, if you just want to check one side, that's okay. You could check the other one. Okay, if you wanted to check the limit as you approach a from the right, if that was a positive or negative infinity as well, okay, you don't have to check both anymore in order to find a vertical asymptote. As long as one side is going up or going down, there must be a vertical asymptote there to cause that drastic shift. Okay, so a vertical asymptote is only at an x value if one of the sides is going towards some type of infinity. And we saw that in the 4 that we did at the top. Okay? So let's check out the one at the bottom. For the function below, find any vertical asymptotes that exist. Justify your answers using limits. Okay? So with this fraction here, how might we be able to figure out a particular x value that might not work? Yeah?
We need to factor the bottom and the top.
Let's factor the bottom and the top. The bottom's kind of the most important because those are the numbers that cause an issue. If you want to factor the top too, that would be okay. So if we factor the bottom, looks like x minus 1, x plus 3. If you factor the top, we got 2x plus 1 and x plus 3. Notice how the x plus 3's would cancel. Okay. So where is an x location that a vertical asymptote might exist? What do we need to check? X equals, yeah?
1.
1. Okay, so based on the fact that this x minus 1 did not cancel, this is a possible vertical asymptote that we need to check. What is the x equals negative 3? The value from the factor that did cancel? If it does cancel, what's showing up on the graph? Yeah. Not an x-intercept, not a 0. You would get 0 over 0, which is a whole. right? If you plug in negative 3 up top, this factor would become 0, and then this factor would become 0. Okay? So based off of what you did last year, okay, you can identify vertical asymptote at 1, hole at negative 3. I know you guys know that. But we need to justify using limits, okay, a calculus reason behind it. So if we're specifically looking at vertical asymptotes, we need to check either side of this x value of 1. Do you want to check the left side or the right side? Doesn't matter. You want to do the right? Okay, so the limit as x approaches 1 from the right. Maybe we'll use the 2x plus 1 over x minus 1 because technically that's what's left after you cancel out the x plus 3's. Okay, so if you were to pick something a little bit bigger than 1 and plug it into your equation, we'd get a positive over a positive. So the right-hand side of this 1 value looks like it's going up, right? Okay, so justify your answer using limits. There is a vertical asymptote at the x value of 1 because you could say the right limit at the x value of 1 is infinity. Okay, as long as you're equaling a positive or negative infinity, you have a vertical asymptote at that location. No longer can you say you have a vertical asymptote because x minus 1 didn't cancel out. Okay, that's how you can identify the value that you need to check, but you have to check it. Okay? A little bit more. This is what you did last year. This is how we're relating it to calculus. Okay? Alright, let's go ahead and check out the next one. Let's check out some other infinite limits here. This time if we are approaching positive or negative infinity. So I think I said before a limit at infinity describes the end behavior of a function. Okay, as you go to the right or to the left, are you leveling off anywhere? Okay, do you have that horizontal asymptote? What's our first step in a limit usually? Plugging it in, right? Now, in terms of end behavior, we do not have the graph of this equation. And we know having a graph is a little bit easier because at least you have a picture. So if we don't have a picture, let's go ahead and think about if we were to plug in infinity, like any other limit we try to do that for, what would we get? It's going to look weird, okay, but let's see what would happen. If you plug in infinity into those x's, let's think what we would get out. Okay. What is infinity cubed? Infinity times infinity times infinity. Yeah, it's still infinity. It's a very large number, right? And if you were to take a very large number and multiply it by -3, how would that change that very large number? Yeah.
Make it a very, very large negative number.
Very, very large negative number, right? So this technically simplifies to negative infinity. A very, very large negative number. And if we look at the rest of the expression or equation here, we have plus infinity minus infinity. Or minus 4, sorry. So what do you think negative infinity plus infinity minus 4 is? Yeah. -4, is that what you were going to say too?
Yes.
Yes?
Something like that.
Okay.
Well, let's just be
What? So I have a -4 and a negative infinity. I can understand the -4 because most of us see negative infinity, positive infinity, those cancel, right? And you're left with -4. Why are you saying negative infinity?
Because it was cubed and then multiplied by 3.
Okay, so this is why infinity is so crazy or kind of difficult to understand or interpret. Let's pick some value for x, like 10, okay? If you were to plug in 10 here, 10 cubed is 1,000, times negative 3 is negative 3,000. We would have plus 10 minus 4. Does that equal negative 4, like we're saying this is? No. This is some very large negative number, right? So what's going on here is visually, I know you guys see negative infinity plus infinity, those should cancel. But this is a larger infinity because, like Ryan said, it was being cubed. A cubed makes something 3 times itself. Not 3 times itself 3 times. So if you take a very, very large negative number and you add something smaller to it and subtract 4, aren't you still a negative value? So this would be negative infinity. Okay, it's going to take us a while to wrap our heads around this infinity idea. Okay, so in terms of a graph, if we had one, this is telling us the further we go to the right, notice how we were approaching positive infinity, our graph goes down. So there is no horizontal asymptote. Maybe there's a slant one, we don't know, okay? But the further you go to the right, your graph goes down. So we'll say graph goes down to the right. So we were checking the right end behavior, the right side of the graph. How does it behave? Which direction is it going? That type of deal. Okay, let's go ahead and try another one. We don't have a graph, so it's kind of hard to determine what's going on the left-hand side. Let's try substitution like we would do for any other limit. If you plug in infinity, negative infinity this time, what's 4 minus a negative infinity? AKA 4 plus infinity? Is that still infinity? Okay. If you plug in negative infinity into the other x, negative infinity minus 3 is still a negative infinity. You're making it slightly smaller by subtracting 3, but it's still negative. And then what about negative infinity and then you add 1? Really, really negative number plus 1. Isn't it still negative? So infinity squared is still infinity, but this is the larger infinity value. Right? Because it was being squared. All the other ones were not. So infinity times negative infinity times negative infinity. What do you think we're left with? We're not really going to get a number value out. A positive infinity, yep. A really positive number times a really negative number times another really negative number. Essentially positive times negative is still positive. Okay? So graphically speaking, even though we don't have a picture, the further we go to the left, okay, we were approaching negative infinity. The further we go to the left, the graph goes up. Graph goes up to the left. Are we doing okay? This can be tricky sometimes with all the infinities. All right, let's try another one. If we plug in infinity, 3 minus 2 times infinity over infinity plus 3. Can we identify which infinity is larger in this case? We knew this one was larger because it was being cubed, whereas the other ones weren't. We knew this one was larger because it was being squared, where the other ones weren't. What do you think?
That is 2 infinity.
It would go towards infinity?
No. The 2 infinity is the big infinity, so go towards the negative because that's a negative in the top.
So you're saying this one's larger?
Yes.
Because it's being doubled?
Yes.
Okay, I can understand that. That's not quite what I was looking for, but I'm trying to think about how can I explain that. Do you notice how neither one of these x's had a power on it, like the other ones did? Okay. Clearly this one was larger because it was cubed, this one was larger because it was squared, but if neither of these have a power on them, they're essentially the same value, right? Try to pick something other than infinity. If you plugged in 10 here and 10 here, wouldn't those kind of stay 10s as you plug them in? Whereas if you plugged in 10 here, it would change to 1,000, right? These are technically the same infinity value. Okay, same infinity. Now I want you to think about, if you're plugging in a huge number and you multiply it by -2 and then you add 3, do you think adding that 3 on the end is having any significance whatsoever on your value? Not really, right? So what's technically going on up here is we have a -2 times infinity. This plus 3, since we have the same value, not one of them was being raised to a power, this 3 is kind of insignificant. If you add 3 to infinity, you're not really changing that number that much. For kind of the same reason down below, if you take infinity plus 3, that addition of 3 is insignificant. You're not changing the value that much. So if these are the same infinities, for instance, 10 over 10, or 100 over 100, or 1,000,000 over 1,000,000, what is that fraction going to reduce or simplify to? Think about it as -2x over x. These are exactly the same infinity. These are exactly the same variable. What are we going to be left with? We're thinking -2. Good. Okay. So in this case, as we go to the right, our graph is leveling off at -2, meaning we have a horizontal asymptote. Horizontal asymptote at the y value of -2 to the right. Okay. Some of you might remember, or at least familiar with, in terms of degrees, if the powers are the same, what's going on. Okay, we're going to investigate that a little bit tomorrow. We're going to come back to this, okay? Infinities can be tricky because it's technically not a number, it's an idea.
Ah, that's how that could work. I like to put subscripts in my infinities.
Do you?
Yes, in order to identify which one is the potential larger one. And I just identified it and roll to that. How my subscripts work is that to whatever power it is the first number, then point, and then whatever it's multiplied by. And if it's to the same front number,